Okay, very good, thank you. So today we will see matter coupling, which we started discussing last time. So we said that we look at then in a global supersymmetry theory, we have a set of chiral multiplets and a number of vector multiplets. It's not really working, huh? The theory is completely specified once you fix the Kähler. Let's try again. So I said last time that if you want to specify a globally supersymmetric theory, then the theory is specified, of course, by the number of chiral multiplets, the number of vector multiplets. For the time being, we are not discussing tensor multiplets or any other kind of multiplet that includes matter fields of a different species. Then you need a real function of the scalars in the chiral multiplet, which is the Kähler potential, and which gives the self-interactions of the chirals. You need a superpotential if you want to give a mass, for instance, to the fermions, and also to introduce a scalar potential. If you give up, as we will do, renormalizability, you can have non-minimal gauge kinetic functions, meaning you have non-minimal couplings between the vectors and the scalar fields in the chiral multiplets. You will need to specify the gauge group, and if you have charged matter, this generically is specified by the fact that you will have an action of the gauge group on the scalar manifold, and this is given in terms of a certain number of killing vectors, specifying the isometries on the scalar manifold that are going to be gauged, which on the other hand, as we will see, are related essentially to the what are called the prepotentials, which are essentially the d terms in the vector multiplets. And then if you have abelian factors in your gauge group, you're also allowed to introduce Fayet-Iliopoulos terms, which are constants, which can introduce an additional source of supersymmetry breaking. Now, the purpose of this lecture is to show you what are the differences that appear in supergravity with respect to global supersymmetry, which are not due to giving up renormalizability. As I said already, by giving up renormalizability, you will have lots of new terms that will appear already in global supersymmetry with respect to a standard renormalizable theory. However, if you go in supergravity, there are additional modifications, and some of which are especially important. I will show you in particular, for instance, that Kähler potential and superpotential are not two independent functions. In global supersymmetry, you introduce the Kähler potential, you introduce the superpotential as two completely unrelated quantities. In supergravity, this is not the case. So in supergravity, these are related. We will see later exactly how and why that happens. Another thing that is important is that, for instance, also the gauging, the D terms, are not independent from the F terms. This is another thing that is very different from what happens in global supersymmetry. In global supersymmetry, you will have F terms and you will have D terms, and these sources of supersymmetry breaking are again completely independent. In supergravity, the prepotentials are related to the derivatives of the superpotential. I'll show you exactly how and why again later. There are caveats as usual, so I will discuss and try to be precise, but generically D terms and F terms are related. And this is a rather important fact because, again, in the literature you can find confusing statements, and especially you can find statements about phenomenological aspects, let's say, or phenomenological aspects of supersymmetric theories or coming from string theory, where these things are not taken into account correctly. Even in the original KKLT scenario, which probably you know, I mean, when people try to obtain the Sitter vacua first by fixing supersymmetry on a fixing the vacuum by finding an anti-de Sitter supersymmetric vacuum, and then breaking supersymmetry by introducing a D term. Well, this cannot be done in a fashion, in a two-step procedure without taking into account that as soon as you introduce the D term, also the dW is going to be affected. So you cannot fix dW to be 0, the F term to be 0 in order to find a supersymmetric vacuum and then break supersymmetry unless you do things very, very carefully and paying attention to what you're doing. The other thing is that Fayet-Iliopoulos terms, which are completely independent in global supersymmetry and appear for abelian factors. Well, first of all, I will discuss briefly that such constants are not necessarily appearing only in abelian factors in supergravity, but especially in supergravity, again, these Fayet-Iliopoulos terms are related to the non-gauge invariance of the superpotential, and they are completely fixed in your theory. They are not arbitrary. Okay? So you see, while you try and describe generically supergravity theory with the same ingredients that you use in global supersymmetry, so we'll still write down a scalar potential, a superpotential, we'll write down the D terms, the Fayet-Iliopoulos terms, and so on and so forth. The difference is that these quantities that we are writing down have relations that they have to satisfy, which are not the same as in global supersymmetry. This changes quite a lot the structure of the theory. So I'll try to review and discuss these ingredients one at a time. So I will start with the scalar potential. And then I'll go on and try and show you where the new features appear. So let me write a picture here because this is going to be useful also for later. So as I said, if you have chiral multiplets, you can interpret the scalar fields as coordinates on a scalar manifold. And on this manifold, you have a metric, which is of course a function of the scalar fields, which is related, well actually let me write it here, which is related to the second mixed derivative of the scalar potential. Now, this means, as usual, no, in differential geometry, that on your manifold, you might not have coordinates that cover globally your manifold, so you will introduce generically different sets of coordinates in different patches. Okay, let's take two open sets, open set A and an open set B, and in each of these, you might also have a different expression for the scalar potential. Okay. The interesting thing is that, though, these scalar potentials on the set A and on the set B must be related by some function which is essentially the real part of a holomorphic function, and this is what is called a scalar transformation. Okay? So Ka and Kb are not completely arbitrary functions, they are related by means of the real part of a holomorphic function. And why is that? Because eventually the metric that you get, especially in the overlapping part of the two patches, should be the same. Okay, and you see that the metric does not depend on this real part of this holomorphic function, because since you have mixed derivatives, either the anti-holomorphic derivatives will kill the holomorphic piece, or the holomorphic derivative will kill the anti-holomorphic piece. So this is fine, and in general, in global supersymmetry, the scalar potential never appears anywhere in your action, explicitly. So even if you have here this structure, that you can define a scalar potential, you can define it differently in each patch, provided that in each patch, the overlapping parts, the scalar potentials are related in this way. The scalar potential is an ingredient which never explicitly appears in your Lagrangian. In fact, if you look at the Lagrangian for the chirals, as we discussed last time, you have a kinetic term for the scalars and fermions, in your theory. We said you might have some mass terms for the fermions coming from the superpotential, and you will have scalar potential coming again from the derivatives of the superpotential. This is still at the rigid level, okay? And you see there is no direct expression where the scalar potential appears, nor there is an expression where the superpotential appears again without derivatives. Okay? Now, what happens when you try and make supersymmetry local? The same thing we discussed in the very first lecture. If you take the variation of this Lagrangian, you will end up having something here. Well, the coefficient is not too important here. Sorry, you will have something here that comes with a derivative of the supersymmetry parameter coupled to some current. Okay? If you remember, we discussed this in the very first lecture, and we said, of course, as long as as we are in global supersymmetry, this is vanishing, so the Lagrangian is invariant under supersymmetry. But now, this is not the case anymore if you go to local supersymmetry. So how did we cure this? Well, we cured this by introducing a new field, a gauge field for supersymmetry, which is the gravitino. And we said the gravitino should transform with the derivative of the supersymmetry parameter. At the beginning, the simple derivative, then this has been improved to the covariant derivative because we will have eventually to couple gravity. And this means that you have to introduce a new term in the Lagrangian, which goes with 1 over mp, so it's Max Planck suppressed, and this is the important point, again, because eventually you want that when the Planck mass goes to infinity and supergravity decouples, you should be able to recover in some way the global supersymmetric theory. And of course, you would like here to have precisely a coupling of this sort, so this is the gauge field of supersymmetry, which should couple, therefore, to the current that in the original variation comes multiplied by the derivative of the parameter of supersymmetry. So in this way, you can compensate this term, but then we said if you vary again the current in this new term that we added, then you have to introduce something that goes with the variation. Well, you get something that comes proportional to the stress energy tensor, which we interpret as the variation of the metric, and therefore we couple, we say gravity becomes dynamical, we'll have a coupling to the gravity theory, plus we said there are some additional terms which I didn't discuss last time, okay, which I'll schematically Z1 and Z2, which again, the structure is important, the coefficients, well, the coefficients are important as well if you want to really prove supersymmetry, but now we're trying to argue what are the new ingredients rather than trying to prove explicitly supersymmetry. And the thing is that in here you have additional terms, which, remember, in this current we had 3 gamma matrices, no? This current was contained derivatives of the scalar fields, and then we had, or rather the variation of the current. The variation of the current contained derivatives of the scalars, something like that, no? And then some epsilon parameter, yeah, something like that. And we had this structure, no? The derivatives of phi and phi star and some gamma matrices, and we said, when you look at and use a bit the algebra, you can reduce those gammas into a single gamma with a metric, and this is what you get here, no, this contribution. But then you also get additional pieces where you have 3 gamma matrices, okay? And this is exactly what I'm going to look at here. In Z1, for instance, I mean, this piece is the piece that I didn't consider last time, which comes with, of course, the gravitino, and then the variation of J, no? That's the part. So we'll have something like the gravitino, 3 gamma matrices, and then I have the terms that come with multiplied by the derivatives of the scalars, and if I have here a number of scalars, then I will also have the metric, no? Because I need something to. Here I was looking at a single scalar, no? When I wrote down the example in the original, in the first lecture when I discussed the Vezdumino action for a single chiral field. Now I have a number of them, so this is what I'm going to have. Then the other thing that I find, if I do that now, is that the supersymmetry transformations are changed with respect to the original ones. No? In the original supersymmetry transformations, I had that the scalar would go into the chiral fermions, and this is what remains. But then I had that the transformation of the chiral fermion was going to be, or maybe there was a factor of 1/2, it's not too important here. I had a d slash phi on epsilon, but now, since I'm introducing also the superpotential, I will have an additional term which comes with the superpotential here, no? Beside the fact that I have higher order Fermi terms if I assume generally interactions, but here I need something that comes with the superpotential in order to generate these terms, for instance. No? As I said last time, all the shifts in the supersymmetry transformation of the fermions are going to be generating the scalar potential. And now let me get the right coefficient. So yes, there was a 1/2 there. And then there is a term that goes like minus 1/2 gi j bar dj bar w and then epsilon. Okay, if this was left, this is left. Sorry if I write as this is too small. Plus, as I said, higher order Fermi terms. So this means that the only reason why I'm mentioning that is that when I vary the current now, I don't just get this term, which is what we saw when we discussed the Vezdumino multiplet, but now I get an additional term which comes from this piece of the variation. Okay, so I get something which is proportional to the superpotential as well, and this is also, of course, mass Planck suppressed because the whole interaction here is mass Planck suppressed, and it has the structure of the gravitino contracted with the derivative of the superpotential. Well, let me write it like that then. epsilon left, derivative of the superpotential, plus, of course, Hermitian conjugate because we want something real. So I get these two terms, okay? And I have to deal with both these terms in order to reestablish supersymmetry. And as I will show you, this first term, Z1, is the one on which I'm focusing now, which has to do with the scalar potential and has to do with the structure of the manifold, is what is going to change the structure of the scalar manifold from scalar to Hodge scalar. Okay? And I will show you momentarily what this means. And this other term instead will be discussed later because, of course, it affects the properties of the superpotential. Okay, this has to do with the superpotential, so we'll discuss it later. So let me focus on the first term. The first term, as I said, is what is going to affect the structure that I have related to the scalar potential and the structure of the manifold. So if you look at that Z1 term, then it contains two derivatives of the, there's the gravitino, I have the gamma matrices, epsilon, and here I have, and this is the part where I want to focus myself, I have derivative of phi, derivative of phi bar, or phi star, whatever, I mean the conjugate, and then the metric. And remember, the metric is also the derivative, let me write it really explicitly, with respect to the scalars of the scalar potential. So you see, that term can be interpreted, depending on how you want to look at it, as the fact that you take some derivative of the scalar potential, let's say with respect to phi bar, and then you have the chain rule here, no? D in d phi I, d in the x nu of phi I. Or you can do it in the other way around, of course. No, it depends which one you like. Either you can do it with respect to the phi or with respect to the phi bar. It doesn't matter much. And actually, in order to get something which has a kind of symmetric structure between the two, you can do the following. No? You can imagine d rho phi bar j, and then you have a d nu of dj bar of k, and then, of course, you can write down plus the Hermitian conjugate if you want obtain the other structure. So you see, now I have this derivative, which is a space-time derivative acting directly on the scalar potential, on the derivative of the scalar potential. And what I can do is integration by parts in order to remove this derivative from here. And clearly, when it acts on the scalar field here, this vanishes, because here I have a fully antisymmetrization in mu nu rho, whereas derivatives are clearly symmetrized. Well, they commute, so if I move the derivative here, that term disappears. So the only terms where the derivative survives is when the derivative acts on the first term. And especially, you see, there is a term which is very suggestive of what we should do in order to compensate for this term. Because after an integration by parts, among the various terms, I will have a term of this sort. D nu epsilon times d rho phi bar j k plus, again, some Hermitian conjugate there. Then one has to be careful with the I factors and coefficients and everything. But the interesting thing is that now you see I have gravitino, gamma matrices, derivative of epsilon. From what we learned last time, how can I cancel such a term? Adding a term where here I have psi bar, gamma mu rho, gamma 5, and again a gravitino. Because the variation of the gravitino is the derivative of epsilon. Okay? This term here looks like, again, the variation of a gravitino. So this is very interesting, because now you see, if I look at that term which I now have to add, the term that I'm adding has an amazing resemblance with the kinetic term. So the term that I have to add now is going to be something, well, okay, again, the proper coefficient will be what will be. But the important thing is that here I can write this thing in this fashion, where Q if you do everything correctly with the proper coefficients and signs, has the following form. Okay? So you see, this object, mu. So if you remember the Rarita-Schwinger action, had a kinetic term. The original Rarita-Schwinger action had a kinetic term with a covariant derivative acting on the gravitino, where this covariant derivative was covariant with respect to the spin connection. Okay? And now what I'm saying is that in order to compensate for the new terms that appear when I make supersymmetry local and I have chiral multiplets, I need to introduce a term of this form where I have this Q, which looks like a composite vector field. You see, this is a composite, effectively transforms like a vector field. But it's really a composite connection, and I will discuss momentarily in which sense this is a composite connection. Composite because this is clearly not a vector field, it's built out of scalar fields. No? It's derivatives of scalar fields. But it appears here exactly in the way it would appear if you now improve essentially your derivative to a covariant derivative, not just with respect to the spin connection, but also with respect to this new connection Q. Okay? So it looks like you have a coupling of a vector to the kinetic term of the gravitinos. So when do you have a coupling of the vectors to the fermions? Generically, when you have that the fermions are charged with respect to a certain symmetry, and that vector acts as a connection for that symmetry. Now, what is this symmetry? And indeed, this is a U1 connection, because if you take a scalar transformation, so imagine that you take a scalar potential and you shift it, as I said before, with the real part of a holomorphic function, then look at what happens here to Q. Q gets shifted. No, it's not invariant under a scalar transformation. Because I don't have the second mixed derivatives of the scalar potential like I had in the metric. I have simple derivatives. So you see, I get I over 2. I have the derivative with respect to phi bar, and then here I have the derivative of the transformation, and of course the anti-holomorphic derivative kills the first piece but keeps the second, so I get dj bar of h bar, and then there I have minus d mu phi I di h, and you see this is nothing but saying that q goes into q plus the imaginary part of the derivative of the holomorphic function that appears in the Kähler transformation. Okay? This is just a derivative d mu of h, no? If you apply the chain rule, simply because the d bar of h is vanishing. Okay, so this is really like a U1 connection, and therefore this means that you should interpret this new term as the covariantization of a U1 symmetry. And of course, what is this U1 symmetry? This is a U1 symmetry that should act also on the gravitino. Now this thing will become, so you eventually want that these scalar transformations are such that your theory does not depend on those, no? Just like in global supersymmetry. In global supersymmetry, that was trivial. You could define different Kähler potentials related by a Kähler transformation. But since the metric depends on the second mixed derivatives, nothing in the Lagrangian will depend on the Kähler transformations. Now, in supergravity, I have an explicit coupling here where I have first derivative of the Kähler potential. So now I risk of having an explicit dependence on the Kähler potential. So how this is cured? This is cured in the sense that, by the fact that if the gravitini transform, so when you do the Kähler transformation, you assume that the gravitini transform as well with the Kähler transformation, and they transform in the appropriate way in such that this connection is the connection that removes the non-homogeneous piece that appears from the derivative acting on psi, then this whole thing becomes invariant. Okay, you will have psi transforms with a phase, psi bar transforms with the opposite phase. Of course, you have the problem of the derivative, but this is cured by the connection. Okay, the usual thing. What is this transformation? Well, this transformation, if you look at the expression there, is that the gravitino should transform with the exponential of something which is going to be, again, Max Planck suppressed. I didn't specify here, or I mean, the proper mass Planck's, Planck mass is everywhere. But it should be Max Planck suppressed because this thing should disappear when you go back to the rigid limit. And then you have, indeed, the imaginary part of this holomorphic function h, times gamma 5. There is a gamma 5 here which is crucial, because this is not a simple U1, it's a chiral U1. It acts with different signs on the left and right components of your gravitino. Okay? So, let me actually get the correct coefficients. So, yeah, no, the Planck mass is essentially hidden here, because when I write down the covariant derivative with respect to omega and q, this is the covariant derivative with respect to omega plus, where do I have it here? Yeah, plus I over 2mp squared. And then I have q and the gamma 5, of course, acting on the gravitino. Okay? So the crucial thing, though, is that when you go to supergravity, the gravitinos become charged with respect to a chiral U1, which is what? Which is the U1 contained in the Kähler transformations. Okay? So what this means from the point of view of your manifold is that actually your manifold has some new structure. Well, this structure was present also before, but it was trivial in some sense. What is this structure? The structure has to do with the fact that on top of your manifold here, you can define a bundle, a complex bundle, a line bundle essentially, whose sections are these functions h. And of course, in the rigid case, this is a trivial bundle. Nothing happens essentially, when you do these transformations. But now you don't have anymore something which is trivial, because the fermions, you will have the gravitino defined in the patch A, you will have the gravitino defined in the patch B, and again, in the overlap of the two patches, the two gravitini, well, it's the same gravitino, but I mean the gravitino field defined in one patch and in the other patch must be related by this transformation. Okay? So you have additional structure, and you might say, okay, fine, I have additional structure, but it affects essentially only the gravity sector at this stage, no? It affects the gravitino. In fact, when the gravitino disappears, when gravity decouples, well, first of all, Max Planck to infinity, this U1 disappears, but the gravitino also should disappear when I decouple gravity, so why should I bother too much? I mean, it's something which is new, which affects really the gravity sector. Well, that's not really true. It affects really the whole structure. And the reason is that, obviously, if the gravitino transforms, in this way, you know that under supersymmetry, the gravitino, and here also now you will have the same connection appearing, of course, transforms into the supersymmetry parameter. So now, if you want this expression to be covariant with respect to this new symmetry, this means that also the supersymmetry parameter should transform. Okay? If the gravitino transforms with respect to a U1 in this way, this should be covariant, of course, which means that epsilon should transform in the same way with respect to the symmetry as the gravitino does, and of course this means that there must be some connection in here as well in order for the covariant derivative to be covariant. Okay? So this means that epsilon also transforms with the same chiral transformation as the gravitino. Yes? This extra U1 at this stage is a global symmetry. The question is whether it's anomalous or not. And in fact, it is extremely important when you gauge the theory to understand whether you gauge this U1 or not. Because indeed, you might get anomalies which spoil completely the consistency of the theory. So that's a very good point. The fact that it is a chiral U1, it's a crucial fact in order to establish consistency of the theory once you gauge the theory. Okay, at this stage it's a global symmetry, so it's not a big deal whether it's anomalous or not. But when you make it local, when you gauge the symmetry, this is a U1 which you might gauge, but if you do, then you have a problem.
Sorry.
Yeah. The connection Q is with respect to this, yes, but this is not a symmetry. pay attention, the difference between the fact that this depends on the scalar fields. Okay, so this is a symmetry that comes from the scalar transformation, but this is not something we are gauging. We are not introducing parameters that depend on the coordinates for such a symmetry. The H functions are arbitrary functions of the scalars. So these are the coordinates somehow which you use in order to define these functions, which also depend on the space-time coordinates. But this is not an ordinary gauge symmetry.
It does not even seem to be global because you introduce explicitly a covariant derivative with respect to the symmetry.
I introduce a covariant derivative here in order to make everything indeed covariant with respect to the symmetry. But again, pay attention to the fact that you have to distinguish here space-time from the scalar manifold. So this is a transformation on the scalar manifold. On the scalar manifold, so phi i's are coordinate on my scalar manifold. Here I have my coordinates, phi I, which are also functions of space-time, but this is something else. I mean, I'm considering this manifold as a scalar manifold in which the scalars are coordinates. And then on this manifold, I have this structure, the fact that I have a scalar function, a scalar potential, which can be defined in different ways in different patches, which are related by a scalar transformation. And this scalar transformation then is the one that implies this U1 transformation on the gravitini, and hence requires the introduction of this connection. But this has nothing to do with the fact that I have a real connection, meaning a gauge field for such a transformation. This Q mu is a composite vector field. It's not a real vector field. When I want to gauge it, when I want to make it local, then I assume that I introduce now a transformation. I have, among the various transformations here, I have this, this symmetry that I make local, and then I will need to introduce in here an additional vector, which is really the gauge vector field for this transformation. So this is a different thing, okay? And then in that case, I start having problems because I have a real gauge vector field, which is gauging this isometry, and then having an anomaly is a problem because in order to quantize this gauge field, the A mu, Q mu doesn't need to be quantized. Q mu is not a real vector field. Q mu is a composite vector field. If I introduce instead a real gauging here with a vector field that couples to this, to the gravitino, and the gravitino is charged with respect to this U1, then in the quantization of this vector field I have problems because I have a chiral anomaly. Okay? Any other question? Why it is U1? This is a U1. I mean, it's a phase.
Yeah, sure, but I mean, why you know that all the possible fields are integer structure?
Okay, no, that's okay, this is a different story. At this stage, this is just a classical theory, so I wouldn't even know what the charges are here. I mean, they're indeed continuous. I mean, this is a classical theory. When you quantize it, then you can check that this is indeed a U1, and then, well, let's see. At the classical level, also the classical level actually I can show you, yeah, sorry, also the classical level, I will come to this later. I can show you that you need some quantization condition, and that the field strength of this connection has to be quantized on even integers. in order to have consistent, again, definition of all the fields, but this depends on the type of manifold that you have, but I'll come to that later, okay? Wait a bit and I'll show you that as well. Anyway, the crucial step, let's see how we are on time, okay, yeah. So, the crucial thing is, if you do the same thing we did in the very first lecture, which is to take the Vezzumino model, now, of course, a number of chiral multiplets, and you make supersymmetry local, introduces, in general, a new term, a new coupling that tells you that the Kähler transformations are not inert now on the fields of your theory. And in particular, we show that on the Gravitino, you need to have a U1 transformation acting, which is inherited from the Kähler transformation. Now, the fact that this U1 acts on the supersymmetry parameter as well in order for this transformation to be covariant actually tells you more. It tells you that also the other fields are going to be charged. Because remember again, yeah, sorry, I erased it, but remember that the transformation rule of the chiralini goes with the derivative of the scalar fields times the supersymmetry parameter. Okay? Plus, you will have additional pieces that depend on the superpotential. Again, I'm being schematic here. Don't trust the coefficients, but it's important to see the structure here of things. And you see here, there are two things. If epsilon transforms in the same way as the Gravitini, since the transformation of chi is associated to d/phi epsilon with the opposite chirality, of course, because there is a gamma matrix in here. So the transformation of the left chiralino goes with epsilon right, and vice versa. This means that the chiralini, the fermions in the chiral multiplets, transform with the opposite phase. Okay? So if the phase goes with a minus here and the gamma 5, here it goes with a plus. Because if this transforms with a minus phase, of course, this should, sorry, if the left transforms with a minus, the right transforms with the opposite, and so you need to have the same sign, of course, for the left and the right epsilon and the left chi. And then you see also that a problem arises here in the second part, which we'll address later, which is the fact now that if this transforms in the same way as epsilon right, now it transforms in the opposite way than epsilon left, which means that if you make this transform in the same way as chi, then you have a problem with this term, unless you ask that the superpotential transforms as well. And this is the crucial point that I mentioned at the beginning, that in supergravity, the Kähler potential and the superpotential are related. Because if the superpotential transforms, this means that when you do a Kähler transformation, you don't just change the Kähler potential, you change the superpotential as well. Okay? But let me get to that in a moment. If you look at the Gagini go with f/epsilon. So since these are two gamma matrices now, you have the same chirality on the left and right hand side, which means that Gravitini, supersymmetry parameter, and Gagini all transform in the same way, with the same phase. And it's the chiralini that transform in the opposite way. Okay? So what is this telling you? This is telling you that your scalar manifold has a different structure than in the global supersymmetric case, because now it's not just the gravitini that transform, but all the matter fermions are going to transform as well under Kähler transformations. So whenever you perform a Kähler transformation, you have that all the fermions are transforming. So all the fermions are sections of this bundle that you introduce on the manifold. So in the global supersymmetric case, you indeed have a complex line bundle, but it's trivial because whenever you do a transformation on the Kähler potential, nothing changes. The fermions are not transforming, the metric is the same, nothing happens. Now though, in supergravity, when you perform a Kähler transformation, the metric of course doesn't change, but the fermions, all the fermions, the gravitini, the gaugini, the chiralini, they all transform under this transformation. So they are non-trivial sections of this, well, fiber bundle on the manifold. Okay? And this is what makes the structure of the manifold different. So it's not just a standard Kähler manifold that you're used to, but it will become, and I will show you the missing last step in a moment, it becomes a Hodge-Kähler manifold. So you have this bundle, this fiber bundle on the manifold, which now is non-trivial. Okay? So of course this means that also when you write down derivatives of the fermions, and in your Lagrangian of course you will have the kinetic terms of the fermions with derivatives, also those kinetic terms are going to be improved, exactly like the kinetic term of the gravitino. You will have new terms, which are again mass Planck suppressed always, which come with the same composite connection Q, in such a way that this kinetic term become invariant under Kähler transformations. Okay? Questions? Okay. Then the second step is related to, well, yeah, I now erased the only formula that I needed. Okay. The second step is related to the superpotential. And it has to do with what I was just saying, that if you look at the transformation rule of the chiralini, this contains a term which seems to transform in the wrong way. Because if now epsilon right and chi left transform in the same way, this term has an epsilon left and therefore transforms in the opposite way. So this means that you need to compensate in such a way that you need to compensate the mismatch by introducing a transformation of the superpotential. And actually, it's a bit more complicated than just giving a transformation of the superpotential, because you see, chi transforms with the exponential of I over 2 m Planck squared, the imaginary part of h. Okay? Chi transforms with this. Epsilon, we said, transforms in the opposite way. So let me actually forget the exponential. There is an exponential of everything here. These are the exponents of my transformation. Okay? On the left-hand side, the exponent is going to be something like that. Here, on the right-hand side, since I have epsilon, I have something that goes with minus. And how can I make the two match? I need W to transform. But now W is a holomorphic function. So W cannot transform with the imaginary part of H. I can assume, of course, that W transforms by some exponential of h with some coefficient here. Okay, this I can do. W is a holomorphic function, so I can assume that it transforms with the holomorphic function h. But this doesn't give me the imaginary part of h, which I have here, and which gives me the mismatch. So how do I make it right? Okay? The way to make it right is to introduce something that again transforms with both h and h bar. You see, here I have something that goes, again, let me be very schematic now. The gamma phi, of course, is on both sides, so I can forget about that. So here I have something that goes with h minus h bar. Here I have something that goes again with h minus h bar, but with the wrong sign, the opposite sign. And the superpotential transforms with h only. So if I have w bar, it will transform only with h bar, with a certain coefficient. So let's say that here I have alpha h bar. How can I make the two things the same? Well, I can make the two things the same if I add something else here, which contains both h and h bar under a Kähler transformation. What does transform with both h and h bar under a Kähler transformation? The Kähler potential. So you see, this means that in supergravity, in order to make things covariant, I need to dress the superpotential. So whenever I have the superpotential, I have to add in front of the superpotential the exponential of the Kähler potential with a certain coefficient, of course. In such a way that the whole thing transforms covariantly. Because if on the left I have h minus h bar, and on the right I need h minus h bar, but I have the wrong coefficient because I have the minus sign in front, W transform with an h bar, K transform with h plus h bar, and then you see that if I choose appropriately alpha, I can flip the sign and obtain again h minus h bar. Okay, and I can make things work. So let me actually do it explicitly for the gravitino. Well, I could do it there as well, but there is an additional complication, which is the fact that you also have the derivative there of the superpotential, and I will come to that in a second. But the same structure you have for the gravitino. If you look at the transformation rule of the gravitino, you have that this has the the standard piece. So let's say the left contains this part, which we know is covariant. Then there is a piece that comes with the superpotential times a gamma matrix and epsilon. And here you have exactly the same problem as the one that I have up there, which is the fact that if this transforms with the exponential of minus one quarter h minus h bar, this has an epsilon right, which means it goes with a plus one quarter h minus h bar. The exponential now I assume that goes like that, so I have an exponential, well, let me put a minus actually, minus alpha rather than plus alpha. It's conventional. Like that. And then what I do is I introduce an exponential of the Kähler potential in such a way that here I write the exponential of beta h plus h bar now. This is the transformation. And then you can put together the exponents, and you see that I need minus a quarter h minus h bar, which should be the same as beta h plus h bar minus alpha plus a quarter h minus h bar. And you can check that you can solve this if you choose alpha equal 1 and beta equals 1/2. Okay? So the crucial thing is that I will justify this term in a moment. But it's the same thing. You can do it there as well. The only difference is that you have to be careful, of course, because when you transform W here, you get also derivative of H. Okay? And of course, this means that we also have to covariantize the derivatives. But the point is that the first thing you have to do is to dress the superpotential, because also the superpotential transforms. So when you do a Kähler transformation, you will also have that the superpotential is going to be by the Kähler transformation, by the same holomorphic function that appears in the Kähler transformation. So this tells you that Kähler potential and superpotential are not independent in supergravity. You see, I could actually choose a Kähler transformation here such that H is the logarithm of W and put the superpotential to a constant. So in supergravity, what you really have is either you have the superpotential, so it's non-zero, or it's zero. If it is non-zero, you can always reabsorb the superpotential in the Kähler potential by a Kähler transformation. And the superpotential then is just a constant, mass Planck cube. Okay, so this is very different from what happens in global supersymmetry. In global supersymmetry, you have Kähler potential and superpotential are two independent ingredients, two independent inputs in your theory. In supergravity, the input is there is or there isn't a superpotential. Is it zero or is it not? If it's zero, then you have the Kähler potential. If it's not, then you have a constant that appears somewhere, and then again the Kähler potential. Of course, you can always write down a superpotential, but you also know that by a Kähler transformation you can always remove it and put it to a constant. So it's customary to keep, of course, the superpotential to match with what you know from global supersymmetry. And of course, you discuss the Kähler potential, the superpotential separately as two ingredients that you specify in your theory. But what you really need in supergravity is only to know whether there is a W or not. Because if there is, you can always put it to a constant by a Kähler transformation. Okay, so these are not independent ingredients in supergravity. Now, the fact that the superpotential transforms clearly tells you that also the derivatives of the superpotential have, or, well, let me say with respect to the scalars, these have to be covariantized. And the way they are going to be covariantized is by means of an additional piece which is going to be proportional to the derivative of the Kähler potential. You see that if W goes into W times the exponential of minus h over mp squared, if I do the derivative, I get the derivative of these, which means that I get the exponential, of course, times the derivative of w, but then I get also minus di of h times the same exponential and w. So I need to get rid of this part in order to make things covariant again, and the way I do it is by adding a derivative of the scalar potential, because when I send k into k plus h bar, since I have the holomorphic derivative, this goes into dik plus dih. The derivative on h bar goes away. So this becomes covariant. Okay? But the essential structure here is that in supergravity, either W is 0 or W is non-zero. If W is 0, then you specify the scalar potential, and this gives you your theory, tells you what your theory is. If it is non-zero, then you can always define an object, which I call G now, which is the sum of the scalar potential plus the logarithm of W squared divided max Planck to the 6. Remember, W has dimension 3, which is invariant under scalar transformation. And you see, since this is the scalar potential plus the logarithm of W bar, which is the same, of course, no? Log of W bar is the same as log W plus log W bar. This is like taking K and transforming it to G by a holomorphic, a scalar transformation, where the holomorphic function is nothing but the logarithm of the superpotential. And of course, this is non-trivial only if W is non-zero. If W is vanishing, then you cannot do that. But if W is non-vanishing, then you can shift the scalar potential by that scalar transformation and reabsorb it into the scalar potential. And so in this basis, essentially, your superpotential is just a constant. Okay? So if you introduce G, so rather than having, so you can either have K and W, or you can have G and WG, the superpotential associated to G, which is just a constant. Okay, you can move it from one to the other by means of a scalar transformation. And of course, yeah, just one last thing. And of course, the metric is still the second derivative of this scalar potential. Please.
Sorry, so in the Lagrangian only G can appear?
Yes. Eventually only G will appear.
You are saying that W appear only in the combination all W times
let me remember now. Wait, because there is the yeah, I think you can always do up to a phase redefinition of the fermions. You can rewrite the whole Lagrangian just in terms of and its derivatives, of course. There might be some further definitions that you have to do, but that's, I think, is correct. Let me just state one more thing, which is about the other term, which I didn't consider at this stage, which is the Z2, and which is the source of the additional term that I wrote down to the gravitino. So, well, this is still related to the superpotential if you wish, but the point is that there is a modification to the Lagrangian that introduces Lagrangian masses and a new term in the superpotential. And this has to do with the fact that, if you remember what I wrote at the beginning, I have a Z2 term, which is mass Planck suppressed, which has the form of the gravitino with a derivative of the superpotential. And if I took left, then this was the bar, plus Hermitian conjugate. Okay, there was a term like that. So what can you do in order to get rid of this term? Same trick as before. Do an integration by parts and move the derivative from the superpotential to the supersymmetry parameter. So you end up with a term of the form psi bar gamma mu nu derivative of epsilon times W bar. This is now what? This is the variation of the gravitino. So this means you add to the Lagrangian a new term which looks like a mass term, you see? Which looks like a mass term, which is of the form psi bar gamma mu nu psi nu, and then in front I have a W bar over m Planck square. Of course, plus Hermitian conjugate. And you remember our discussion of the pure gravity with the cosmological constant. We said when you have a cosmological constant, the way to introduce a cosmological constant is to shift the gravitino transformation rule by an order G term, to introduce a mass for the gravitino of order G, and then a cosmological constant of order G square. So now we have a mass of order G. You see, this is a complex coefficient in front of psi psi. So remember also the discussion we had about the fact that G had to be complex, the coupling constant. So now this coupling constant is field dependent. But if you have that, then this means you have to shift the gravitino transformation rule with a term that depends on this W, and this is exactly what I discussed previously. And you will have a new term in the potential. So consistency will require you to do the same steps we did for the case with the pure cosmological constant. So the gravitino will not just have the covariant derivative of the supersymmetry parameter, but now has a new term which goes with gamma times the supersymmetry parameter, and in front there must be the G, the coupling constant, which in this case is the superpotential, and which will come with a certain coefficient now, which I already forget, but it's not too important, plus 1 over 2 MP W. And of course, for the same reason that we discussed before, there must be the covariantization of the expression requires that we introduce here, that we dress the superpotential by a Kähler, by an exponential of the Kähler potential. And the potential, the scalar potential now, if this was in global supersymmetry the sum of an F and a D term, where the F term was simply Gij bar diw dj bar w. Now, of course, this has to be modified in gravity by the addition of a new term, which will come with a minus, because remember what we discussed, no? When we discussed the pure cosmological constant term, if this is the coupling constant, which gives also the mass of order g, then you have a negative contribution to the potential of order g square. So this Vg is actually 3, anyway, w squared, w bar, so this is 6, so I need a mass square. Okay, the coefficient, if you remember, there was a factor 3 also for the coupling constant. It's exactly the same reasoning. That's why I also have this factor of 1/2 here, in order to have the same factor of 1/2 as in the case with the pure cosmological constant that we discussed previously, so you can match the two expressions immediately. Of course, this has to be covariantized, so there must be an exponential of the Kähler potential. This has to be covariantized, so there has to be an exponential of the Kähler potential, and the covariant derivatives have to be improved to covariant derivatives. Okay? So everything now becomes dressed because of the fact that you want this symmetry to live invariant to your Lagrangian. But now the important thing is that you have, on top of the positive contributions which you already have in global supersymmetry, you have a negative contribution. You see, the negative contribution is mass Planck suppressed. The positive contributions contain pieces which are mass Planck suppressed, but which go either vanish because they are the covariantization in the limit, or they go to 1 in the exponential, but it still remains in the rigid limit, of course, the derivative of w squared. And the other thing is that you can rewrite this. Let me call the sum. Let me forget for a second the d terms. Let's just look at the terms that depend on the superpotential. You can rewrite this potential as the exponential of this g times m Planck square Gij bar dig dj bar g minus 3 m Planck to the 4th. So as I said, you can reabsorb the superpotential into the Kähler potential by a Kähler transformation, so you can also, you're allowed, if you do that, to rewrite the potential in this fashion. So you see that there is a dependence only on g here. Well, okay, and the part that depends on the superpotential here is nothing but a constant. Okay? So, Kähler potential and superpotential in supergravity are not independent inputs. You can absorb the superpotential in the Kähler potential by a Kähler transformation. Now, what about gauging? Any question on this? Okay. Yep. Yes, the U1 that we mentioned before, the chiral U1, is actually part of the full line bundle, you have really a line bundle here, and the H is the section of the line bundle. The U1 is just the phase in there.
So the gauge field, but on M scalar is like the derivative of the scalar, the symplectic potential, right?
Sorry?
The first derivative of K is like our gauge field on M scalar. I'm not talking about this, right? Just to match.
No, not exactly. The composite vector field Q is not simply the derivative of K. No, you've seen that it's a mixture of the two. I mean, you have derivative of K minus the derivative minus the bar. So again, it depends whether you're considering the complex or the U1 really. But yes, it's a composite vector field as I mentioned. Yes. And it's it comes from the derivative, if you wish, of K, yeah. But I don't know exactly what was the question, but I mean...
The question was about the fact that you promoted the derivative of W, that is a function on M scalar.
Yes.
To a covariant derivative that, and the piece...
Yeah, but yeah, okay, I understand now the question. Yes, I promote the derivative of W into a covariant derivative which contains the derivative of K. And that has to do with the fact that this is a complex function, and you have a complex line bundle on the manifold. This is a section of that line bundle, and hence you have indeed that decay is the part that compensates for that. Just like if you take the imaginary part of decay, you get the Q vector field, the Q composite vector field. Okay? Yes. Yes. Okay. But the main message is, beside all the details, which you can also look more carefully later, the main message is that there is new structure appearing with respect to rigid supersymmetry, and that is important because eventually this will tell you that not all rigid supersymmetric models can be transformed into supergravity models. And this is a very important statement because imagine that you want to cook up for some reason a phenomenological model that explains something and explains something perfectly. You will have your Kähler manifold that maybe has certain properties, and then as soon as you couple this to gravity, this becomes inconsistent. Because the manifold that you have to use for supergravity is not just a Kähler manifold, but is a Hodge-Kähler manifold. I'll come back to this, I'm afraid not today, next time with an example that shows you explicitly that. But let's see, maybe I still have time. At this stage, it's still arbitrary, but I will show you that there are constraints. That's exactly the point. And it will come naturally soon. I mean, let me talk about, now this is number 4, gauging. Let me talk about this first, and then I'll give that example, either today or next time. Let me talk about the gauging of the isometries, because there is something that usually is not done already in global supersymmetry. And I've seen time and again seminars or papers where people say, okay, and I do supergravity because in supergravity then I can introduce a gauging with a scalar manifold that is complicated, in which these isometries are the Killing vectors and so on and so forth. This has nothing to do with supergravity. This is giving up renormalizability only, whereas supergravity imposes additional constraints on top of that. So let me discuss this. So assume that I have a scalar manifold, which is the scalar manifold of my chiral manifolds, and then I have isometries on the scalar manifold. Now you know that the isometries are going to build a Lie algebra, so I will have that these isometries are going to be some Killing vector, or be labeled by some Killing vectors. And the point is that Killing vectors, so if I have my scalar fields, this will transform with some parameters times these Killing vectors. The thing is that these Killing vectors are not arbitrary, cannot be arbitrary, because of course what I want here is to preserve supersymmetry. I want to introduce a gauging, so I want to make some of these global symmetries of my theory, I want to make them local, but I want to do that in a way compatible with supersymmetry. So if I want to do it in a way compatible with supersymmetry, I have to realize that these Killing vectors cannot be arbitrary Killing vectors. They must be holomorphic Killing vectors. Why I want these Killing vectors to be holomorphic? Because I want that the split I'm introducing on my manifold in complex coordinates, phi and phi bar, remains preserved by the isometries that I'm looking at. Simply because the supersymmetry transformation tells me that the chiral fields phi and the anti-chiral field phi bar transform in opposite ways. So I cannot mix phi and phi bar. So I better not gauge isometries that mix phi and phi bar. I should take Killing vectors which are holomorphic, combinations of the Killing vectors, if you wish, that you have on your manifold, which are holomorphic, in such a way that you preserve the complex structure. Okay, so you want to preserve, so this is the first requirement, so I want to preserve the complex structure. Okay, I want to preserve the complex structure because I want to be compatible with supersymmetry. If I don't do that, then I will break supersymmetry at some point because I'm mixing phi and phi bar. The other point is that I want these isometries to preserve the scalar structure. Meaning that the action of these isometries on the scalar potential must leave the scalar potential invariant up to a scalar transformation. Because, again, in my Lagrangian, I have that the scalar potential appears naked, the superpotential may or may not appear, but again, I want the whole structure to be invariant. And we know that if we have that the scalar potential transforms with a scalar transformation, then the other fields will transform in such a way that the whole Lagrangian remains invariant. So the scalar potential does not need to be invariant under the isometries, but for sure it should not transform in a way that is different from a scalar transformation. I can allow some non-invariance of the scalar potential, but such that the scalar potential transforms with a scalar transformation. And this means that also the superpotential under these isometries does not need to be invariant. But it should transform, again, if this is the infinitesimal transformation, it will be like that, by a scalar transformation by the holomorphic function that acts on the superpotential. Okay, this is the finite expression, this is the infinitesimal one. Okay? So, you know that on a scalar manifold, since you have a complex structure, you can split your coordinates in phi and phi bar, but a Kähler manifold is not just complex, it's complex with respect to a certain complex structure, certain almost complex structure, which must be integrable. But it's also symplectic in the sense that you can introduce a two-form, which is going to be simply, well, let me write it like as a two-form in this way. Which is closed. And if you wish, this, again, well, depends now which one to impose first, but this follows from the fact that this is the derivative the second mixed derivative of the Kähler potential, so you can always write JFD of something locally. Okay? You can always imagine that either this is D of this thing with respect to the del of this thing, or the del bar, depending which one you pull out. Okay? So now the fact that you want your isometries to preserve the complex structure and the Kähler structure of your manifold means that your isometries should preserve the Kähler form. Meaning that if I take the Lie derivative of J, I should get 0. This follows from the fact that I want my isometries to preserve the complex structure here as well as the Kähler structure. Now, if you write this in differential form language as the Lie derivative can be written as the inner product with respect to, well, let's say the isometry I. Let me do it like that. The isometry I after taking the differential of J plus the differential of taking the inner product of J with the isometry vector I. But dj is 0. And this has to be 0 in order for the isometry to be a good isometry that I can gauge, because I want the isometry to preserve my Kähler form. So this tells you that the inner product of the Kähler form with your isometry should be locally the derivative of something. Okay, and this is how you introduce the prepotentials and the D terms. And this is where the relation, this tells you that at least locally, you have that II of J is going to be D of some prepotential function. And these are the prepotentials that define your D terms. Now you see, what I'm doing here is completely general, doesn't assume anything on the Kähler manifold at this stage. And this is interesting because, of course, the fact that the D terms, for instance, when you have a standard linear action, is given simply by phi, the generator phi bar, where T is the generator of your linear action on the fields, follows from what I'm writing down just by taking the Killing vector to be a linear matrix acting on the scalar fields and following the computations that I'm doing. But this is far more general because now I can have a very complicated manifold with isometries that are whatever they are, and I can still make everything go through. Okay? And this has nothing to do with supergravity at this stage. This is true. Well, okay, this part here has to do with supergravity. Everything else is true also in global supersymmetry. In global supersymmetry, of course, you don't have an action on the superpotential of the Kähler transformation, so this better be invariant. And supergravity can be non-invariant, and you get that additional piece. Now, what is this expression here? Okay, let me write it here. Now you see the inner product simply means that you replace the leg here with a Killing vector. And since you preserve the complex structure, you can either rewrite it in terms of the holomorphic part or the anti-holomorphic part, and you will get two different expressions. So one is this, and the other this. And of course, they are one, the complex conjugate of the other. Here, I just replace. Now I do the inner product, so I replace this with psi. On the right, I have the derivative. So this derivative I can obviously split into the holomorphic plus the anti-holomorphic. Since I preserve the complex structure, the holomorphic part should be equated with the one that has a d phi on the left, and the anti-holomorphic derivative should be equated with the one that has an anti-holomorphic leg. So I get these two equations. And eventually, you can also see that, well, they are one, the complex conjugate of the other. And you can also, by using the fact that, again, this is the derivative, the second mixed derivative of the scalar potential, you can also find an expression for the prepotentials. So this tells you what is the relation between the Killing vectors and the prepotential. And now I can find the expression for the prepotential, because if I replace in here the second mixed derivatives, since this is holomorphic, you see I can pull out the derivative, because del of psi bar gives 0. And then you see that the prepotentials are defined in terms of the scalar potential in this way, up to some holomorphic functions, in this case anti-holomorphic functions, because I'm equating two equations, two terms with a derivative. And of course, again, I can do the conjugate expression from here, so that eventually I can write down an expression which is real, which is the fact that these prepotentials can be written as 1/2 minus I psi bar del bar k plus the conjugate plus I have these functions well, maybe I should not call them with the same name as there. Let me call it H. Okay. Which also tells you that you can arbitrarily introduce an imaginary constant in your H, which will not affect the form of the prepotentials. And these are the Fayet-Iliopoulos terms, but now I can show you something more, and the fact that in supergravity these are not arbitrary. So, let me summarize before moving on and closing the argument. So, already in global supersymmetry, the fact that I want to gauge some of the global symmetries of my theory means that I have to take holomorphic Killing vectors, because I have to preserve the complex structure and I have to preserve the scalar structure. This is not there in global supersymmetry. This is something that will appear in supergravity. Now, the fact that I have a scalar form tells me that these isometries will be related to prepotentials. So for each isometry that I gauge, there is a prepotential, and this is the term that generates the D term in your Lagrangian and your supersymmetry transformation rules. The D terms are nothing but the moment maps of your isometries. Essentially, I have a symplectic structure, And to each isometry, I can associate a moment maps, like in classical mechanics, and these are the D terms eventually. Now, these prepotentials, though, here I still have some ambiguity. I have these holomorphic functions, these holomorphic integration functions that are arbitrary at this stage. Now, gauge invariance imposes an additional constraint on the prepotentials. So this is one relation that goes from the Killing, from the prepotential you can obtain the Killing vectors in this way, or from the Killing vectors you can obtain the prepotentials in this way, we said. I hope I'm getting the coefficients right, but I mean, okay, something like that. However, gauge invariance tells you that these prepotentials are constrained. In particular, there is a condition which is called the equivariance condition. Which is nothing but requiring gauge invariance, essentially, which the Poisson brackets of these prepotentials via the structure constants of your gauge group. And this tells you that now these functions are not arbitrary anymore. Because the algebra will fix this, obviously. No? You cannot anymore have arbitrary functions in there and change them without affecting this algebra. And the interesting thing is that this tells you, by the way, that the possible Phi-Heliopoulos terms, the possible constant coefficients, imaginary constants in these HIs, are fixed by this structure. So you might have constant contributions, imaginary constants in your prepotentials that are needed because of the equivariance condition when you have a non-abelian theory. And in my notes, you can find an example of that. As well as the fact that if you look instead at the generic case of supergravity, these Phi-Heliopoulos terms are not arbitrary anymore because of this request. Because the fact that the superpotential has to change. Because from the expression that I mentioned here, for instance, well, or if you want let me write it in the other way. Sorry, let me write it in terms of the potential, just like that. Let me get the right coefficients, just a second, and I'm almost done. Where is that now? Yeah. So the fact that the prepotential should transform, in that way, this tells you that this can also be written down as the derivative, the covariant derivative of the superpotential divided by the superpotential. Remember that the covariant derivative of the superpotential, because of what we said before, because of the transformation rule, is given in this way, which means that for a non-trivial superpotential, you see, when there is a non-trivial superpotential, the F terms, the derivatives of the superpotential, and the D terms, these prepotentials, are related. So if you turn on one, you will turn on the other one as well. So if you break in supergravity generically, of course there are exceptions, but generically in supergravity, whenever you have D-term breaking, so this is non-zero, you will have F-term breaking, and vice versa. Of course, you can have very non-trivial examples in which you have dW, which is non-zero, but in a direction which is different from the ones that you gauge. No? If the contraction of the Killing vector with the derivative of the superpotential is non-zero, sorry, zero, then you can still have that the prepotential are zero, even if dW is non-zero. Or you can have special limits in which dW over W is finite, even if dW is vanishing, because also W is vanishing at that point. Okay, so you can have pure, what I'm saying is that it's not that you cannot have pure D-term breaking or pure F-term breaking in supergravity. What I'm saying though is that because of this relation, the generic situation is that when you break supersymmetry with an F-term, you will break it also with a D-term and vice versa. Okay, if you have gauging, of course. The situations where only one of the two appears with the gauging are very peculiar. So either, as I said, the F terms are in directions which are different from the one that you gauge, so that the contraction is vanishing, and then you can have D term breaking, but not, sorry, F term breaking, but not D term breaking, or you can have P non-zero, even if dW is zero, if W is also zero at that point. Because in the limit you might get something finite. So this is rather non-trivial, okay? Okay, so since my time is up, what we saw today is what are the ingredients that are needed in supergravity that are different from global supersymmetry. You see that the Kähler potential now appears naked, as well as the superpotential appears naked. And this has to do with the fact that the structure has changed. The scalar manifold is the same, it's still the Kähler manifold, and has a line bundle on top of it. The problem is that this line bundle, of which the superpotential and the fermions were independent before, now, or better, were trivial sections of before, now the superpotential and the fermions are non-trivial sections of this bundle. This means that you have to covariantize all derivatives, this means that you have to introduce all sorts of new couplings. You generate a mass term for the gravitinos, you generate a potential, a scalar potential now that has a negative contribution. You also see that in the gauging, you have a non-trivial relation between D terms and F terms, and because of these, you see that the Fayet-Iliopoulos, which are the imaginary constants essentially that you introduce here, are related to the superpotential, to the non-invariance of the superpotential. So once again, they are not arbitrary. They appear only if the superpotential is not gauge invariant. Otherwise, you don't have the Fayet-Iliopoulos terms. So all this is coming from supergravity. As I said, this structure of the manifold now gives you constraints on the manifold, which are not too strong, but I will show you in the next lecture, an example in which, for instance, the Kähler potential, if this manifold is very simple, it's just a sphere, for instance, so it's topologically non-trivial, then you see that the Kähler potential in global supersymmetry can have a coefficient which is completely arbitrary. In supergravity has a coefficient that has to be quantized. So again, when you go from global supersymmetry to supergravity, there will be constraints, and not all the Kähler manifolds that you have in global supersymmetry are allowed in supergravity. And this is true for minimal supersymmetry. When you extend supersymmetries, you go to n equals 2 or greater, then you will have even further constraint, and you will have a much bigger difference in the sense that while in global supersymmetry, any supersymmetric theory with n equals 2, 3, or 4 can be expressed as a special case of an n equals 1 theory, in supergravity you cannot. You will see in supergravity when you go to n equals 2, n equals 3, n equals 4, these are theories that cannot be written as a special n equals 1. And this is the reason why in supergravity you have to learn all these theories separately. because the structure of the scalar manifolds, the structure of the couplings are really different. They cannot be written in the same way. Okay? Any quick question? Okay, then anyway, we have a question session this afternoon, so I'll see you later.